Hello everyone, my name is Sahil and today I'll be talking about some online learning problems where the costs are vectors. So this is joint work with Thomas Kesselheim, who's a faculty at University of Bonn. So let's start off by recalling the classical online learning setup where we have T time steps and N actions. Each time step, the algorithm has to select an action or a distribution over actions where action I incurs some cost. So maybe action I incurs a scalar cost between 0 and 1, CIT. The point is the algorithm doesn't know these costs before selecting the action. So the algorithm first selects an action or a distribution and it incurs this cost. And now depending on whether we are in the full or the partial feedback model, we get to see this entire cost vector or just the output cost of our action. The goal of the algorithm is to minimize its total cost. In particular, it wants to minimize its cost with respect to an opt, which is a fixed distribution over actions. So X star, this benchmark opt, is no longer allowed to change its distribution every time step. It plays the same distribution every time step. And the question is, how well can we do compared to this? So this difference is called the regret. And this problem has a long history because it appears in many applications. And in particular, we know for the full feedback setting, we can get like a square root t kind of a guarantee. And in the partial feedback, we can get a square root n kind of times the square root t kind of a guarantee. The focus of today's work is what happens if these costs, rather than being scalars, what if they were vectors? In particular, so what is this online learning with vector costs? We have again t time steps and n actions. Each time step, again, we select one action or maybe a distribution over these actions. And what we incur is a column, a vector cost. So where this is a matrix CT and ith action incurs this ith vector. So we'll incur a CTXT expected cost. Good. Again, the problem can be studied both in full or partial feedback models. You get to observe just this entire matrix or just this output. And what's your goal? Your goal is to minimize some norm of your total cost vector. So summation over T CTXT is the total cost vector. You get to what you want to minimize is some kind of a norm of it, maybe the L infinity norm. In the paper, we also study LP norms. So what you want to minimize is your norm minus that of a fixed distribution, X star. Good. And again, so the problem can be studied both in full or partial feedback models. And what if we have stochastic or adversarial inputs? And a priori, it's not even clear if sublinear regrets are possible. Good. So let's first look at some motivation for this problem. So one motivation comes from because it's a variant of online load balancing, the classical online load balancing, where the setting is similar. You have T jobs and D machines. In each time step, which is basically a job, you have n ways of scheduling this job. So you can complete this job in one of n ways. Depending on which way you complete it, you're going to incur some vector cost. So think of these machines not necessarily as distributed, different, but maybe they are like the same physical machine. So you have a RAM, you have a CPU, you have a GPU. So depending on how you schedule the job, it might put multiple loads. So it might put loads on each of the dimensions, not necessarily on a single dimension. So you incur a vector cost. And so the algorithm has to select an action. And what it wants to minimize is the L infinity norm. So this is also popularly known as the make span. So the maximum load of a machine you want to minimize. And this problem has a very long history. And even like LP norm variants of this problem has a very long history. Many people have studied it. And so what's known from all these prior works is that, yeah, you can again get like some log D competitive ratios or something for this problem. There are some crucial difference, however, from online learning. So in the online algorithms community, like all these online load balancing problems, usually this cost matrix is revealed to you before you play an action. Whereas in online learning, as I was saying, like you get to see these costs only after you play an action. Full feedback or partial feedback, whichever be the case, you always first choose the action. Moreover, similarly, because in the online algorithm, you get to first see the costs. So you also have a higher, like a stronger benchmark where you compare yourself to the optimal policy. Whereas in online learning, we have a weaker benchmark, which is just a fixed distribution. But both the models make sense depending on the application at hand. So we believe like all these like load balancing problems, they also make sense if we have to play an action before we know the cost matrix. So that's one motivation. Another motivation to study this online learning with vector costs come with its connections to bandits with knapsacks. So this is a popular problem which was originally defined in 2013 and in the stochastic variant, and the adversarial variant was defined last year in Biomodelic et al. So you can think of this as nothing but some kind of a maximization variant of the online learning with vector cost problem. where again you have t time steps and n actions. Each time step you select an action or a distribution. You incur a vector cost as before. So you have a vector cost ctxt. You also receive a scalar reward, which is rtxt. Similar to classical online learning setup, you receive a reward and you incur a vector cost. The problem can again be studied in full and partial feedback model, where you receive both of them, get to see them, or you just to get to see the outputs. The goal of the algorithm is to maximize the reward. So it wants to maximize the reward. So the costs, notice, are not appearing in the objective, but they are appearing in a constraint. So we want to maximize the reward while satisfying the budget. So the algorithm wants that the summation over ctxt, the L infinity norm, basically in each dimension, the budget consumed is at most some given b. Okay, so accordingly, we can now define a regret, which is the difference of what opt is minus your alg, the reward of both of them. So here, opt is any fixed distribution, which receives some rt x star reward. Notice the summation is only from t equals 1 to some time step tau star, where opt runs out of budget. So wherever this policy x star runs out of budget. So both opt and algorithm, whenever any of them runs out of budget, they stop receiving any further reward. So the question is, how can we minimize this regret? And okay, in this paper, we also defined an LP variant of this problem, where you want to satisfy this budget constraint, not as L infinity norm less than equal to B, but LP norm less than equal to B. Good. And the problem is interesting, this bandits with knapsack, just because it has many, many applications. It's like dynamic pricing as well as ad placements with budgets. So, okay, what are our main results? So I'll state our results under this assumption that the algorithm knows opt, the value of opt. So this assumption is just to simplify it, like how the results are stated. Many of the results extend, but I don't want to get into those subtleties. So first, what happens in online learning with vector cost? So in the stochastic setting, we get sublinear regrets. So sublinear regrets are possible. But in the adversarial arrival model, we get a competitive ratio. So for L infinity norm, for example, which is the most important case, we get a log D competitive ratio, which is also typed. So we show that you cannot do anything better. And what do I mean by competitive ratio? A log D competitive ratio basically means that the cost of our algorithm, the L infinity norm, is at most like log D times that of the optimal algorithm. So I have one remark that the stochastic results also follow from the work of Agrawal and Devanur from 2014. So the value of our result is more that it's saying like pretty much the same algorithm works both for stochastic and adversarial setting. So ours is a very different algorithm. Theirs was more like a UCB-based algorithm. So now we also study bandits with knapsacks. So we, in some sense, we are basically giving a reduction from bandits with knapsacks to an online learning with vector cost. So we get similar results. That in the stochastic setting, there are sublinear regrets, and in adversarial, we get tight competitive ratios, which is log D. So again, stochastic results were already known from this 2013 work. For adversarial setting, the problem was first studied in the last year, 2019 paper of Vimalika et al. They obtained a order D competitive ratio, which we roughly exponentially improve basically to log D. They only studied the L infinity. We also studied the P norm variants of the problem. Okay, so for the outline for the rest of the talk is I'll just give first the high level approach, and then I'll give some specific ideas for both the problems that we do. Okay, so online learning with vector cost, we have to minimize the L infinity norm of the total cost vector, or LP norm in general, as compared to a fixed distribution over actions. So first, some intuition on why simple greedy algorithms with respect to L infinity norm don't work. So here's a nice example to keep in mind. Suppose there are just two actions, where action 1 incurs a 1 minus epsilon cost in every dimension. So you have D dimensions. In each dimension, it incurs a 1 minus epsilon cost. Whereas action 2 incurs the cost of 1 in only one of the D dimensions chosen at random. Now, if you're being greedy with respect to L infinity norm, and suppose your initial load is all zeros, even if you know everything, you'll choose action 1, because it will increase your L infinity norm from 0 to 1 minus epsilon, whereas action 2 increases your L infinity norm from 0 to 1. So a greedy algorithm would like to choose action 1, but in reality, you should be choosing action 2, because in the long run, it's incurring much less load. So greedy algorithms are omega D competitive, whereas you want to do much, much better. So we remember in this setup for infinity norms, we wanted a log D competitive ratios. And you can also construct examples that you cannot do better than log D. So okay, what are our ideas? Our first main idea is a standard one, which basically is to not work with the L infinity norm, but work with some smoothing of it. In particular, this the softmax function. So, which is a standard smoothing. So, which basically removes all these corners in the contour map, and it converts it into some smooth corners, where the smoothness can be controlled by this parameter epsilon. It has benefits because it gives both additive approximation to the L infinity map, as well as it has some stability properties that the gradient doesn't change very fast. So you can take Taylor expansions and all those things. So this is a standard idea. And in case you're wondering, for LP norms also we have to do some smoothing, but the smoothing function that we use, we take it from Molinaro's paper from Soda 2017. So we use his smoothing. Our second main idea, which is in some sense a new idea, is to somehow convert this vector problem into a scalar problem. In particular, what we do is we define these surrogate scalar costs, which are given by the gradient of your psi function times at the current load times some cost matrix, the incoming cost matrix. So these scalar costs, I'm calling this the surrogate scalar problem. So what our algorithm is, just use these scalar costs and feed them into a classical no-regret algorithm. So a classical algorithm for just the scalar problem, online learning problem, and take those actions. So as you might notice, I mean, in some sense, what we've done is just a reduction from the vector problem to the scalar problem. So our algorithm doesn't even care what exactly is the feedback model, because the same feedback model will be used here in the classical setup. So whether you are in the full feedback or banding feedback, we'll use accordingly the same no-regret algorithm. The main challenge just becomes like, why does this scalar surrogate problem that we have defined, why does it have anything to do with the actual problem? So I've defined this abstract problem. This is the algorithm. Why is this reduction legit? So, okay, I'll give you some high-level ideas. So let's first start off, okay, this is the smooth potential that we were using. So just from its definition, we can bound my eventual load by this potential, which I can write as some of these differences, which by using gradient stability of this function, I can bound it by this. Where CT is nothing but the cost of my scalar problem, which is given by the surrogate, by the gradient. Good. So these inequalities are fine. Now I could use the no-regret property to bound this summation over CTXT and compare it to the benchmark, the optimal solution, CTX star plus regret. There are some main challenges, however. So the first challenge is that this regret needs to be against an adaptive adversary, simply because this cost CT, they depend on my current load. So CT is defined as the gradient at time step t minus 1. So because these costs depend on how your algorithm is evolving, the regret bound has to be against an adaptive adversary, which is not so bad because, okay, we know all these regret bounds even against adaptive adversaries. The bigger challenge is, okay, why does this surrogate problem, these surrogate costs that I've defined, why does this have anything to do with the optimal solution? Because the optimal solution might be taking a very different trajectory. It need not be taking what your algorithm's load is right now. It could be very different. Why does it have anything to do with what your algorithm is doing? So our main technical lemma is actually that we are able to relate this surrogate cost to the actual opt. So from the last slide, we basically know that we need to bound summation CTXT. Our main technical lemma is actually that, okay, in both the stochastic as well as in the adversarial case, we can bound this summation CTXT by some kind of opt plus some regret terms. So I won't go into the proof of this lemma, but crucially, so they rely on some non-trivial inequalities. In particular, in the stochastic case, we use some inequalities by Molinaro, and in this adversarial case by Karyanis. Both of them were originally designed in the online algorithms community. But we are able to apply that even for online learning problems. And once we have these inequalities, we just feed it into this bound for the load, and we're done. So good. So now a quick idea on how we handle bandits with knapsacks. So the idea is just to Lagrangify the constraint. So our hope is that we want to reduce this problem to the online learning with vector cost problem. And what we do is we Lagrangify the constraints and move it into the objective. So this idea of Lagrangification has appeared before. And for example, it also appeared in the Modlik et al. Paper. But the way we Lagrangify has changed. So we use the Lagrangification as given by this gradient, as you were using in the online learning with vector cost. Once we have this, and we just run the classical scalar online learning algorithms. In the adversarial case, the proof pretty much immediately goes through. Just we have to scale down our solution from X star to X star over log D, and remember the budget constraints are now we have to strictly satisfy them. We are not allowed to violate them. In the stochastic case, the idea is to add a dummy source This idea already appeared in the 2013 papers, so we are using basically the same ideas. For LP norms, one has to be a little more careful because it's special coordinate, so you have to define new norm. And that's to conclude. So we obtain sublinear regrets in the stochastic and competitive ratios, tight competitive ratios in the adversarial setting. And one of the nice open questions is, can we achieve the best of both the worlds using a single algorithm? Thank you.